All right, welcome to the final session of the first day of SOSP 2015. We've got a great session on concurrency and performance, and to start us off, we've got Veselin from ETH Zurich, who's going to tell us about user-defined aggregations.
Thank you. So my name is Veselin Raychev. I'm a PhD student at ETH Zurich, and this is joint work with Madanlal Musuvathi and Todd Mytkowicz at Microsoft Research, where I did an internship. So I'm going to talk about parallelizing user-defined aggregations using symbolic execution. So the goal of this work is to answer questions using big data. And one particular kind of data that we are interested in is user logs. So such logs are available in big companies, say Microsoft, Google, Facebook. They have logs of what their users did. But the same approach can be done for any other kind of logs that, for example, a program outputs or some other process. So we'll be looking at query logs of some imaginary website, and we will be looking at what is the user behavior of this website. So for example, in our case, we'll be grouping by user session, and then we'll be interested what the user would do on such a website. So one row that you see there is, so one column actually, is all the queries that were performed by a user. And let's imagine this is some shopping site, and the user does some searches, the user does some purchases on the website, and then the user reads reviews in between. So these are queries, and we may be, these are logs, and we may be interested in a lot of queries about the user behavior of this website. So for example, we may be interested in how many queries how many events were there for each user. Or we may be interested in how many reviews did a user look at between doing a search and a purchase. So what did make a user do a purchase? Another kind of question is, how long did it take between a search and a purchase? How long did the user decide to do a purchase? Or we may be interested of what kind of searches did users do and then didn't do a purchase, or what kind of searches they did so after that they did a purchase. So all kinds of behavior, in this case of users, in many other cases, maybe other events coming, is what we'll be answering. And our goal here is to parallelize these queries. So maybe you saw in the beginning I did group by, and then there was some parallelism there. But we will be extracting even more parallelism. We want to extract as much as parallelism as possible. So within one group of events, we would like to extract additional parallelism there. So this is a sequence of events performed by one user, and we would like to parallelize finding this pattern in this sequence of events. So with our tool that is called SYMPLE, you will be able to run these queries even with one single user on multiple CPUs and on multiple machines. So then I told you we would parallelize, but there is the question, how hard is it to parallelize for a user? How hard is it for a user to use SYMPLE? So here is example of this query that you can write that finds the number of reviews between search and purchase in the logs of such a shopping site. And this would be the code that you would normally write. So for each record that you see in the input, in the user records, depending on its type, you do some counting, for example, for the number of reviews that the user looked and so on. So to do this, normally, we would introduce a variable num reviews, and then we would set it to 0 when there is a search, and we would increment it on a review. We would have a Boolean that will say whether there was a search. We set it to true if we do search, and then when we do a purchase, we check if there was a search before the purchase. And if there was a search, we would actually accumulate the result somewhere. So we would accumulate in some vector of integers, say, there was some session of search purchase, and we are counting how many reviews the user read. So this is what you would do. This program is completely sequential. So you don't do anything for parallelism so far. So now the thing that you would do in order to use SYMPLE is change the int, bool, and vector to Symint, Symbool, and Symvector. So these are symbolic equivalents of the concrete types, and that's everything that you have to do. And you have to then call SYMPLE with the right flags. So there are, of course, great benefits to this. The same code is used for sequential and parallel computation. You don't introduce new kind of bugs. And it's much easier to maintain as a result. So with that simple usage model, we were able to extract parallelism. So I want to tell you first, what is this kind of parallelism? It's kind of new type of parallelism which actually breaks dependencies as opposed to finding independent computations. I will tell you what is this symbolic parallelism, then I will tell you what are these data types that you saw, Symint, Symvector, Symbol. And then finally, I will show you some evaluation, both on a single machine and in a MapReduce setting, to show you what are the benefits of parallelizing using symbolic execution. So first, let me tell you what is symbolic parallelism and why is it different than other parallelism that we've seen, that is available normally with existing techniques. So first, I want to show you a little bit of notation, just to give the notation what it would be. So we have the variables in our computation, MapReduce, search down, and the vector of results. And then we have the program. And these variables, their actual values, we will call it a state. So when in computation, stays in some state S. And then we see an input record. So let's say the input record is this blue square. So this is a transition that is done from this state to another state if we see this record blue square. This transition is described by the code that you see below. And then you get into a new state, S prime, which is, we would say, T, denoted with the blue record of S. So this is the resulting state once this record is processed. So with this notation, now I will show you why is it hard to parallelize, why this parallelism, why such query running this code is not readily parallel. So you start from an initial state, then you see a record, then you get to a next state, but it depends on the previous state. You do, again, get another record. The next state also depends on the previous state. And you can go on, and then you get to the final state. So data dependencies are a problem. And in fact, almost every single, if you look at the program, you would see that almost at every position, you actually depend on in what state you were when you go to the next state. So it is really that you have these data dependencies as you process the records. So this is why it's hard to parallelize. But you can think, well, if I was actually implementing, I was just summing the numbers. This is already handled by existing systems that can parallelize such queries. Like almost all SQL engines, if you give them sum, they would know how to parallelize the sum. And this is because they know that sum is commutative and associative. And this is why they parallelize them. Well, there is a problem. You write custom code, and actually what I've shown you before is neither commutative nor associative. So it cannot be that you just take some system that handles commutative aggregates and just plug in these kind of pattern searching into such a system. So we need something different than what would be readily known as ways to parallelize. So that's why we introduced the symbolic parallelism. And the goal here is to actually reorganize the computation such that we can extract this parallelism. We can break the dependencies from one state to the next one. And here is how it roughly looks like. So we have the sequential computation. This is what it would be if we execute it on one thread or one process. And what we would do is we would take out some of the records, say the second half of the records. And on the first part of the records, we would just execute as if, and then we would get to a state S that gets from this computation. In parallel, we want to execute similar computation, but then we don't know the state from which we would start. So let's say we start from a symbolic unknown state X. And then we see the records. So we see yellow, yellow, and green record. So the final result would be applying these transitions. First, yellow, yellow, green transition on this state. And this would be the result if we would execute this to the final state. If we would want to get to the final state, we have to compute this function. But what we would do, since we don't know the state from which we start, we would instead just compute the function on X, and we would return this function. And then when we combine, we would just call that function on the state S, and then we would get to the final state. So it is equivalent to as if we were doing sequential computation, except that in parallel, we computed this function on X. And this is what is the symbolic execution doing. So here is an example. Let's say we want to implement max And this is the code that you would write for max. It's, again, sequential code. If my current state is less than a record that I see, then I set the state to what is the record. So this is finding the max. Again, this would be if we would execute the code sequentially. So from initial state to the final state, every single state depends actually on the previous state. Every time we're comparing the states. So we have, again, this sequence of like dependencies from one state to another. We perform part of the computation on the first thread, and then we want to compute in parallel from an unknown state X. So we don't know what was the maximum so far, but we want to update it. So what we do is we process records, and then we want to return the function on X. And if we process one record, the value 2, the function that we want to return is essentially the following. If X was less than 2, then 2 is the maximum. Otherwise, it's X. So we want to essentially return this function. And if we would process all the records, we would return some function that is more complicated, that would handle all the records there seen by this parallel execution. And finally, when we combine the result, we would take this function f prime that we computed symbolically from state X, and then we would apply it to the concrete state S, which is in this case 9. As you can see on the left side, I think. Yeah. And then you would get the final result 9. So, of course, there is the question, I don't want this f prime to be very expensive to compute. If this f prime actually was as expensive as processing the records, it would not work. So we want compact and efficient representation of this function. And in fact, you can see maybe that a relatively compact representation is, I have many records that I process in parallel, but I can just say if X was less than 8, which is the biggest of the records, the result is 8, otherwise it's X. So such a representation is what we care about. So if we have such a representation, we can do a pipeline that would process data in parallel. So what we will do is we would split the data. The first task is going to execute concretely, so it's going to get, say, the maximum 8, and the other tasks are going to get some functions being computed. Like for task 1, it's like X less than 7, 7, otherwise X. For task 2, similar but with 9. And so then we would combine them. So we would put 8 in the place of X for the output of task 1, and then we would get 8 there. We would do this for task 2 and so on. So in the result, after we combine, we would get the final state that we would get if we would, as if we were executing it sequentially. So now I'm going to tell you how are we going to compute these symbolic summaries. How I'm going to ensure that the functions are as simple as possible. So there are two very key insights in computing these symbolic data types. So we're looking at the representation of the function, and we are looking such that this representation is computed as if we are doing symbolic executions on programs. So this is a technique that is used for checking correctness or finding bugs. And we would combine it with an idea from abstract interpretation where there is a special domain of a specific shape of the formulas that we're looking at. So we will be looking at formulas that would be described in the following way. Path constraint implies a function. So if we have some condition in the input, we would have a function on the X. And we would be building these path constraints as if we were doing symbolic execution by going through all paths of the computation, of the code that executes symbolically. And we would care about the shape of this function f and the shape of the path constraint to stay in some specific form in a similar way as in abstract interpretation. There are domains there that say, like, if I want to check correctness of some programs, I have different domains that can check, for example, if values stay in some interval, if some values are odd even, and so on. So this is our main insight. And these techniques both come from correctness and from verification. But now we use them for performance. So how we can use them for performance? is something I'll show you with the data types. So the data types are actually the reason why we can use something that is normally very slow, something that executes for hours just to show the program correct, to be useful for performance. And so I'm going to show you one of the types that we have, which is symbolic integer. And it has a very specific shape. So it says if x is in an interval LU, then the result is a times x plus b. And so this is one symbolic integer, and in order to have computation with one symbolic integer, we actually store 4 constants only, LU, A, and B. And with these 4 constants, we are able to keep formulas of this shape. So what does it mean, formula to be in this shape? So for example, if I want to say that the state holds a concrete value B, always this value B, no matter what input it came from, I can write it as if x between, say, min_int and max_int, then 0 times x plus b. If s stores a symbolic value x, so this means it's exactly as the value that you would put there in the input state, you would write again, if x is between minus and plus infinity, it's 1 times x plus 0. So it stores the value x. And then we define transformers. So this is similar to abstract interpretation, where depending on the instructions that you see in the program, you say how the values of this symbolic data type or abstract domain they are changed. So for example, if we see assignment to a symbolic integer of a value, say 7, we would set on the right side of the formula 0 times x plus 7. So we would set it to the concrete state 7. If we would increment a symbolic integer, we would increment the value b and not change the value a. If we would do a check in an if condition, we would see with the value that we are checking whether we would actually intersect the interval in the path constraint LU with the constraint set by the if. So in this case, if u is more than 5, we would cut the interval to 5 when we enter the if branch. When we enter the else branch, it's equivalent as if they were checking to be more than 5. So this is what are our transformers of the symbolic integer data type. There are more operations that we can perform on symbolic integer. For example, we may want to add 2 integers. And they may actually have different values, x1 and x2, for the states s1 and s2. So what would be then the shape of the formula when we add 2 symbolic integers? So the answer is it actually has to leave the shape. It cannot stay in the x between a and u equals, implies ax plus b. So what we do there is we actually disallow it. So we say you cannot add 2 symbolic integers. You can add symbolic integer to a concrete value that you read from the input, from the record, to a constant. But you cannot add it with another symbolic integer. And this limitation seemed to be OK limitation for a lot of queries that you would care about. There is another instruction. So for example, if you would compare 2 symbolic integers, then the path constraint has to be now in some relational domain. We don't want to enter into relational domain. So we again disallow it with a type checker. So we only allow certain operations. We stay in this shape, and we are guaranteed to give exact answer to questions. What would be the value of the symbolic integer, of an integer starting from a symbolic state x? So there are other data types that follow the same idea. Symbolic Boolean is like symbolic integer with 2 states. Symbolic enum has some fixed number of states. Symbolic vector is a vector in which you can append, and it keeps symbolically the prefix of the vector. Symbolic predicate is another type which compares one record to the last record and returns true or false. So same idea, several data types. In fact, with these data types, we have found you can write a lot of things. So data types, they can be composed. So if we have multiple symbolic variables, say in one structure, and you want to operate with all of them, they all stay in the shape of path constraints implies a formula. So a structure of such symbolic variables just means that when all the path constraints of the variables are satisfied, the result is the vector of the values of the functions. So the same construct works also with composite types. So overall, if you have these predefined data types, Symint, Symbol, Symint, and so on, and you're allowed to combine, and we actually allow you to write new data types. In case you need it for some reason, we don't know yet what queries would need more types. But if you need for some reason to not keep the integers with interval domain, but maybe if you want to somehow keep relations between them, you can add more types in our system. And then we enable you to write aggregates like this one, complicated aggregates that would check for a certain pattern in logs data. So I want to show you what is the benefit of using symbolic execution to parallelism. What is the gain of symbolic parallelism? So in order to answer this question, we looked at query logs that we could find available on the internet. So we collected logs from GitHub. We found a data set of Redshift called Redshift dataset, which contains queries for an add system. And then we also performed benchmarks on data sets available at Microsoft, Bing and Twitter data set of like logs for the Bing search engine and tweets respectively. So here are example queries that we can answer with such kind of systems. So we can say things like on the GitHub data set, we may be interested what people do before they delete a repository. Or we may be interested in how long does it take for people to actually merge a pull request. So once a pull request is requested, how many other operations on the repository happen between the pull request is closed? In the Redshift dataset, we were interested in, are there advertisers that operate in only one single query, in single country? Or was there an outage? We call it outage query. Was there a time in which advertisers were not advertising, or not showing, ads were not showing for an advertising? So these are the kind of queries that we can answer with such user-defined aggregates. And if you would try to write parallel code for them, it would be kind of tricky. You have to handle a lot of corner cases. And if you would write sequential code, it's just sequential. Existing approaches cannot parallelize it. So these are the queries. I will show you these 4 queries. The paper has more. And here is how these queries would look like. So we write these queries in C++. It's a fairly small amount of code for each of them. Maybe there is some 20, 30 lines of code to actually call MapReduce, and there are 10 lines of code to write the user query. Then there is the SYMPLE library that we have written in C++, and there are backends that you can call. You can execute the query on a single machine. We support this. We export the multi-core parallelism there, or we can ask Hadoop with Hadoop streaming to call into our binary and perform the query. And of course, we want to extend it. The approach is not really limited to Hadoop or to anything specific in the MapReduce. So we want to expose, for example, Spark interface for this in the future. So here is how it looks if you would compute on a single machine. So this is throughput in megabytes per second. As you can see, it goes quite high. So it's far more than the speed of hard disk. And these are the 4 queries that I've shown you before. And the blue bar is what is the sequential throughput that you would get if you would execute the query on one single CPU. Then the next 3 bars are what would be if we would do symbolic parallelism with 1, 2, and 4 threads. And even for the first thread, we assume we start from state X. We assume we don't know the concrete state from which we start. So just so the threads do exactly the same thing. So as you can see, you pay a little bit of price for doing symbolic execution, and then things catch up by the fact that now your code parallelizes. So this small gap is the overhead from symbolic execution. So it's roughly like in the 20-ish%. This is how much you pay for having the 4 integers instead of 1 integer, to do Symint instead of int. Now, I told you that we actually also improve MapReduce. So this is what you would do if you have this query for user logs, and then you would want to encode it in MapReduce without having SYMPLE, and having sequential aggregation. So what you would have to do is you would have all the input in the mapper and you would have to group by user session. So you produce the sessions for each group, for each user. And then this essentially shuffles all the records from the mapper to the reducer, where in the reducer you would sequentially find the pattern in each session, in each user session. So as you can see, a lot of data is shuffled between the mapper and the reducer, and usually this is done by external sort or hashing, so not very, very fast and efficient. I mean, very, very optimized, but certainly excessive computation going on. If you would use SYMPLE, what we would do is we would execute the query in parallel already in the mapper. So in MapReduce, sometimes they call it combiners, because in the mapper itself, we can execute part of the aggregate. So then we only send the symbolic summaries, which are small function representation of what is happening in each mapper for each user. And then in the reducer, only thing we have to do is we have to combine these functions and output in a file the result. So here is what happens with the data. So if you would do, the blue bar is how many megabytes does a query shuffle from the mapper to the reducer if you would encode it in a naive MapReduce. And the red bars is what would be the amount of data that you shuffle if you use SYMPLE. As you can see, around 2 orders of magnitude. So 172 times reduction is what we see on one of the queries. In fact, there is more reduction on some queries in the paper. Now, there is the end-to-end latency. So this is if we would execute it on Amazon Web Services, so we took instances there, you run Hadoop, and you take the data from the S3 storage on Amazon. So this is the end-to-end latency. It's from several minutes, it drops by around 30% if you would use SYMPLE as opposed to MapReduce. So you would wonder, like, I told you we're going to save you a lot of things, and now there is 30% decrease. But there is a good reason for this. Once we remove the bottleneck of shuffling data from the mappers to the reducers, there is the next bottleneck coming, which is reading from S3. And what happens is that we're actually reading a lot of data from these logs and throwing most of it away just to handle the query. And there is a solution for this, which is to either compress the input with some very efficient compression, or to throw away all the columns of the record that we would not use. And so what happens if you would do this is you would get like around an order of magnitude improvement now using SYMPLE. So in summary, I showed you what is symbolic parallelism. I told you the data types, the reason why it actually helps and it's very fast. I told you how we're going to actually verify that symbolic parallelism is relatively efficient by type checking. I've shown you efficient implementation, and with this, I'm ready to take questions. Thanks for the attention.
Hi, this is Yang Tang from Columbia University. I'm very curious about your representation of the symbolic variables. So if I understand correctly, you cannot represent like x times x, like I squared?
So we can represent, we can do multiplication by a value that you read in the records that you process. But you cannot do something like take the current state and square it. So, but this would be like, I would say, very strange functions that you would want to compute on data.
And can you represent strings?
Yes, but depending on what you want to do with strings. So we have the symbolic vector, so if you want to say concatenate strings, that's not a problem. If you would want to compare like whether some string changed from one record to another, you can use the type that I showed called symbolic predicate, that depending on whether, say, one string changes from one record to another, then you would set the predicate to true or false. You would branch depending on this.
So do you have an estimate about how many real-world user queries can be represented in your symbolic variables?
Yeah, so I mean, the whole project came from ideas that people actually ask these kind of queries in big companies, say Microsoft. So there are at least several thousand queries that are potentially parallelizable with this
And
approach.
out of what? Like what percentage?
What? Sorry, what?
What percentage of the queries can be represented?
I mean, as far as I know, there were only queries that talk about some percentiles. So far, we didn't figure out exactly how to parallelize with this approach. Almost all other queries that were done on sessions of user logs, we could parallelize, essentially. But of course, we are looking for more users. If somebody comes and says, I want to ask this question, and it cannot be parallelized, we will be really happy to see if adding a data type would fix it in some way.
Thank you.
Hi, Stephen Sherrod from Data61. So I assume that since you've moved a lot of the work from the reducers to the mappers are going to see an increase in CPU load. Given this, how does this affect the performance of other services that are also running on the mappers? Is there now more CPU contention? Is that going to be a problem for scalability?
I don't think this is actually a problem because I mean, the mappers and the reducers are working in the same data center. We're essentially saving CPU, not. So you're paying this 20% performance penalty for symbolically executing. But on the other hand, you're saving so much time in sorting. And this sorting was otherwise done by the mappers and the shuffle phase and so on. So in fact, you're saving data center resources. And we have experiments with internal cluster at Microsoft where we are saving on CPU quite a lot.
Okay, one more quick question. So you mentioned, okay, thanks.
We're going to go one last question.
Hello, Miu from Shanghai Jiao Tong University. I have a question about the data splitting. How do you define the partition size?
How did I find? Where to partition? Or?
You said that the first step is to split the data.
Yeah, so it doesn't matter where you partition because the symbolic execution works just from the way it is partitioned already.
So just the same like the original MapReduce, right?
Yeah, so we rely on Hadoop to partition the data.
Okay,
I mean, the files are partitioned actually as originally. Yeah.
Okay, thank you.
Thanks.